For the last 3 years, every engineer building a voice assistant or transcription workflow has been trapped paying what the industry quietly calls the two-stage speech tax. First, you stream audio into an acoustic model like OpenAI Whisper or Deepgram to get raw text. Then, because humans naturally stutter, repeat themselves, and ramble, you're forced to pipe that messy transcript into a secondary large language model like GPT-4o, Mini or Claude 3.5 Haiku, just to strip out the filler words, format numbers, and correct mid-sentence revisions. That second hop doubles your latency, triples your API bills, and introduces another catastrophic point of failure into real-time voice loops. Tonight, Google DeepMind officially eradicated that entire architectural paradigm. In a surprise release candidate dropped direct from Mountain View, DeepMind launched Gemini 3.5 Transcribe, a specialized, native multimodal speech foundation model family accessible via 2 high-throughput developer endpoints, Unary batch via the Interactions API, and sub-second live streaming over WebSockets. With an average word error rate ranking in the top 5 globally on the Artificial Analysis Index, native zero pipeline disfluency, stripping across 85 languages, and a streaming price point slashed to under a penny per minute, the economics of conversational AI just fundamentally reset. In this masterclass, we are breaking down the 3 critical vectors every builder must understand. First, the underlying dual-endpoint tokenization architecture and how smart mode eliminates the secondary LLM layer entirely. Second, the raw telemetry shootout against OpenAI Whisper, GPT Live Transcribe, and dedicated speech providers like Deepgram and Assembly AI. And third, the production deployment blueprint you need to build hyper-low latency voice agents while navigating the 10-minute session cliff. If you develop AI agents, automate enterprise audio, or deploy developer tooling, what you are about to see changes the technical calculus of conversational voice forever. To appreciate why Gemini 3.5 Transcribe is causing such an immediate shockwave across developer communities, we must examine the core architectural flaw of legacy automatic speech recognition. Historical models like Whisper treat speech as an isolated acoustic translation problem. They convert audio spectrograms into discrete phonemes and probabilistic tokens, entirely blind to high-level semantic intent, pragmatic context, or the speaker's overarching train of thought. If a speaker changes their mind halfway through an utterance, Whisper faithfully transcribes both the mistake and the correction, forcing downstream software to guess what was actually meant. DeepMind approached this from the exact opposite direction by repurposing the native audio understanding transformer architecture originally forged for Gemini 1.5 and 2.0. Rather than chopping audio into disjointed acoustic slices, Gemini 3.5 Transcribe ingests audio tokens directly at a fixed density of 25 audio tokens per second into a cross-attention transformer that models conversational semantics and vocal acoustic features simultaneously. DeepMind exposed this engine through 2 distinct API endpoints engineered for opposite ends of the latency spectrum. The first is Gemini 3.5 Transcribe, deployed over the Unary Interactions API. It accepts pre-recorded audio files up to 60 minutes in duration, streaming the entire acoustic representation into DeepMind's tensor clusters to emit structured, grammatical text at over 10 times real-time speed. The second endpoint is Gemini 3.5 Transcribe Live, a bidirectional streaming interface running over persistent WebSockets. Here, developers push raw PCM audio chunks in 20 millisecond frames, and the model emits finalized text segments with sub-second time to first token latency. This introduces a counterintuitive trap that has quietly cost enterprise voice platforms thousands in wasted infrastructure. Trying to optimize voice latency by renting faster GPUs for Whisper doesn't eliminate the fundamental round-trip penalty of sending text to a secondary LLM for cleanup. This brings us to the model's most potent technical breakthrough, its dual decoding paradigms, Smart Transcription mode versus Verbatim mode. In traditional speech systems, asking an engine to clean up speech meant fine-tuning an acoustic model to drop sounds, which consistently resulted in drop proper nouns and corrupted technical jargon. Gemini 3.5 Transcribe solves this by embedding linguistic reasoning directly into its beam search decoding. When you toggle Smart Mode on, the model actively tracks discursive syntax in real time. It strips out verbal disfluencies and conversational fillers like and, without altering the natural sentence cadence. But more impressively, It performs inline semantic self-correction. Consider a common real-world edge case. An executive says, let's schedule the board review for Tuesday. Wait, actually make that Wednesday at 2 in the afternoon. A standard speech model outputs the exact messy transcription, which breaks calendar integration parsers. Gemini 3.5 Transcribe resolves the contradiction in flight, emitting, let's schedule the board review for Wednesday at 2 p.m. It automatically normalizes currency denominations, dates, phone numbers, and markdown list structures directly in the streaming output. Conversely, for legal depositions, court reporting, and compliance archiving, where legal evidentiary standards require exact verbal fidelity, developers can activate verbatim mode. Verbatim mode disables semantic pruning, capturing every stutter and audible hesitation, while providing millisecond-accurate word-level timestamps and speaker diarization, identifying up to 8 separate speakers across the audio channel. On top of both modes, DeepMind integrated custom vocabulary biasing, enabling developers to supply an array of up to 1,000 specialized domain terms, proprietary code identifiers, or medical compounds that the decoding beam prioritizes with zero phonetic drift. Now let's examine the objective telemetry published on the Artificial Analysis Word Error Rate Index and the academic FLEURS multilingual benchmarks. In the automatic speech recognition space, word error rate, or WER, is the gold standard metric representing the percentage of words deleted, inserted, or substituted across standardized datasets. In the latest Artificial Analysis AA-WER index, which evaluates engines against challenging real-world audio featuring regional accents, ambient background noise, and telephony compression, Gemini 3.5 Transcribe secured the number 5 rank globally. For non-streaming batch transcription, it registered an average word error rate of just 2.6%. On the live WebSocket streaming endpoint, where models have zero look-ahead buffer and must commit to tokens with minimal algorithmic delay, it maintained an exceptional 4.0% WER. To contextualize these figures across international deployments, DeepMind submitted the model to the Multilingual FLEURS benchmark spanning 85 distinct languages. Non-streaming batch processing achieved an aggregate 5.04% error rate, while live streaming held steady at 5.50%. But here is the critical takeaway that the raw leaderboard doesn't show. Legacy speech benchmarks penalize models that strip disfluencies because they grade against verbatim ground truth transcripts. When evaluated on semantic accuracy, meaning whether downstream AI agents correctly executed user intent, Gemini's smart mode dramatically outperforms traditional verbatim models because it completely eliminates the ambiguity caused by stuttering and conversational false starts. While the technical benchmarks are impressive, the factor that will permanently alter the landscape of voice engineering is the economic pricing model. For the past 2 years, OpenAI Whisper has been the default baseline for budget-conscious developers at $0.006 per minute of audio. Dedicated speech vendors like Deepgram Nova, 3, and Assembly AI charge comparable rates between $0.0065 and $0.0077 per minute. But the hidden financial trap was always the post-processing step. When you add 3 cents per minute for a fast language model to parse and format the transcript, your true operational cost ballooned to 4 or 5 cents per minute. DeepMind has completely disrupted this cost curve. The batch Gemini 3.5 Transcribe endpoint is priced on exact token usage. 25 audio tokens per second at 0.3 of a cent per minute, combined with roughly 175 text tokens per minute at 0.2 of a cent, yielding an effective blended cost of approximately half a cent per minute, undercutting Whisper while delivering pre-formatted, production-ready text. Even more dramatic is the streaming endpoint. Gemini 3.5 Transcribe Live operates at a blended estimate of $0.009 per minute. Compare that directly to OpenAI's GPT Live Transcribe endpoint, which costs $0.017 per minute. Gemini is delivering real-time, bidirectional, streaming transcription at nearly half the price of OpenAI, while eliminating the need for secondary LLM cleanup entirely. For startups running tens of thousands of hours of call center analysis or live voice agent interactions, this collapses monthly compute expenditure by over 70% overnight. This release is not merely an isolated developer API. Google is deploying it as the unified acoustic backbone across their entire consumer hardware and software ecosystem. On Android devices, Gemini 3.5 Transcribe powers the new Rambler smart dictation mode in Gboard. Instead of forcing users to speak like a 1990s dictaphone, Rambler allows users to speak in unstructured, free-form voice memos, which the keyboard instantly synthesizes into clean, publication-grade prose. Inside Google AI Studio, the model is integrated directly into build mode, enabling voice vibe coding where developers describe complex UI components, refactoring logic, and terminal commands completely hands-free while the system executes code generation in real time. In the macOS desktop ecosystem, DeepMind integrated the model into the Gemini apps, speak-to-window architecture, fusing screen-grounded visual context with low-latency voice instructions. And within the coming weeks, Google will deploy native in-browser voice input directly into Google Chrome, allowing users to dictate into any web form field with zero external plugins. By testing and stress testing this model against hundreds of millions of daily consumer voice interactions, DeepMind has hardened the architecture against ambient cafe noise, wind distortion, and poor microphone hardware far beyond standard laboratory test sets. Here is the tactical architecture blueprint for engineers and founders looking to exploit this release in production. First, address the architectural session constraint. Gemini 3.5 Transcribe Live strictly caps WebSocket connections at 10 minutes per session. To build continuous, uninterrupted voice agents, you must implement a client-side sliding window buffer. At the 9-minute mark, your client must spin up a secondary WebSocket connection, buffer incoming audio frames, and perform a seamless crossfade handover once the active sentence boundary terminates, ensuring zero dropped audio packets. Second, leverage custom vocabulary biasing aggressively. When deploying speech agents for developer tooling or medical workflows, feed your schema definitions, API function signatures, and domain dictionaries into the 1000 token bias array during connection handshake. This guarantees that specialized identifiers like Kubernetes pod or amlodipine decode with 100% accuracy. Third, be aware of the documented precision trade-off. Enabling word-level timestamps in batch mode introduces a slight degradation in transcription accuracy due to constrained decoding beam schedules. If your application does not strictly require subtitle alignment, keep timestamps disabled to maximize textual fidelity. Finally, embrace the zero pipeline architecture. Strip out your legacy Whisper plus LLM post-processing workers. Migrate your streaming ingestion to Gemini 3.5 Transcribe Live and redirect that save latency and capital into your agent's core reasoning loops. Subscribe to AI Enthusiast for real-time architectural breakdowns of the frontier models redefining technology.